Namaste students and the listeners. Let me start today's interesting discussion with a newspaper article that I had read months ago and had written off as largely insignificant with respect to the examination preparation. Although it generated a small question in my head. The Hindu in January 2025 published an article talking about the career in material science and engineering. It did talk about a lot of options that are available in the polymer science and the different domains of the material sciences, only making me wonder if it is so good with respect to the opportunities that it throws. Why does it not normally occur to me that the engineering students that I interact with having taken material science as the specialization? As if in a very conspired interconnection, few months down the line, I came across another article that kind of vindicated my perspective. Here, Times of India in July 2025 writes the article, "Material Science Struggles for Space in Hyderabad Engineering Colleges." In a way, I stood vindicated. And it talks about that why, if at all, there could be some reasons this is happening. Interestingly, there was another article published in India Today which talked about the meet that happened of the IIT directors in Chennai, talking about how the youth today might be getting driven more by the herd mentality and may be given some of the very productive areas a miss. And in this particular discussion, they highlighted some of the key industries which the students of the present age might not be given the due or proportionate importance. Semiconductors, which anyway I think has caught up, but materials, chemicals and sustainability, they say that is understaffed and with lesser admissions. Now, when it came to recording this lecture today, when I was contemplating on this particular issue, it just occurred to my mind, despite me having not giving it the proportionate importance, if we see the entire history of the mankind, we have had all the defining moments in the anthropological evolution dictated by some of the important material which has triggered or catalyzed the evolution of the mankind thereafter. To list out some, the development of the stone tool is considered as the biggest starting point wherein the tool usage and thereby capitalizing or exploiting the nature and its bounty is started. To be followed by the wood, the bronze, the paper, gunpowder, iron and steel, the silicon, a major defining moment, the plastic, and the way it revolutionized the entire world in a most unthinkable manner for us. So much so it has today led to becoming a big menace that we have to deal with. And in that very sequence, the development of some of the polymers which are made up of carbon called the graphene and the different three-dimensional structures created out of it. In this very sequence, people, today we are discussing the all-important topic of Nobel Prize in Chemistry 2025 that has been awarded to 3 scientists who also possibly have ended up developing a material that could trigger a major evolutionary upheaval in the human science. Namely, Susumu Kitagawa, Richard Robson and Omar M. Yagi. What have they been awarded the Nobel for? For the development of metal organic frameworks. It may seem to be a complex Draculian jargon. I will try to de-jargonify it, if that is a word. But before that, let me quickly give you a round trip of your school days science that you basically studied. People, when it comes to the various chemical substances, I believe you have studied the chemical materials into organic and inorganic. Now, why was the term organic called so? Because for a lot part of the history of chemistry, it was believed that anything organic is necessarily derived from biological organisms. But later it was also proven that it might not necessarily be biological in origin, it could be synthesized in the lab also. And the definition of organic chemistry got a bit more refined. I am sure almost all of you know organic molecules and organic substances as the ones which are made up of elements like carbon, most importantly, hydrogen, nitrogen, oxygen, phosphorus, sulfur, etc., and the various chemical combinations they can exist together in. And it is these organic molecules, people, that may exist in multiple structures, and that is the reason why carbon was chosen to be the element to make life in its most diverse and beautiful form. Now what we see, that the organic molecule can be a linear chain of it, or as you might have all studied this cyclic structure called benzene, it could be circular, or not circular, cyclic rather, as well as many cycles connected to each other in what we may call it as polycyclic. These terms will not be an impediment to understand the entire stuff. And then inorganic would largely involve the other elements, including the metals. Now you see, the entire organic chemistry you might have studied in your school science. All the chains of carbon forming methane, ethane, propane and so on, nothing required in the understanding part here, just know that okay, there are these molecules. And then as I told you, the ones which can get cyclized and chained up to create multiple other possibilities of the structure creation. Now, one special type of molecule that got discovered and then changed the entire chemistry altogether, and this is going to be important, are called coordination compounds, or coordinate compound rather. Coordinate compounds. Let us keep it simple. Coordinate compounds are those which may have any atom of any element at the center, and it is connected with many other compounds by a specific bond in chemistry. You might have read about covalent, non-covalent bond, a specific type of bond called coordinate bond. No detailing required, just know a chemical bond. And it is this which is called as the coordinate compound. And then we found, after the discovery of the coordinate compounds, people, can you just understand it through some basic animation? Imagine here is an element, what you see is an iron atom, and it is connected with many of the other molecules and compounds which are called as ligands, which are bound together. And it is this entire thing which is called as the coordinate compound. Now, for the discovery of these coordinate chemistry, way back, over 100 years back, rather 110 years ago, there was this fellow who got the Nobel Prize, Nobel laureate, Alfred Werner. Hardly did he know that the work that he did then would also become critical for the Nobel Prize to be awarded 100 years later. So what is this award all about? But before that, one of the classical most coordination compound that we know of is what that is there in our blood. I am sure all of you already know about hemoglobin. It is a protein which is present in our red blood cells, responsible for carrying oxygen from the lungs to the different parts of the body. Hemoglobin, wherein it is being shown by these colored tubes, has got a coordination compound inside called as heme. It is this which is the coordination compound that's there called heme. You can see a metal at the center connected through the coordinate bond, as I told you, with this entire molecule. Please remember, nothing of these structures and all are important, just the concept. So coordinate is a central atom surrounded by many other organic molecules, bonded by the coordinate bond. Fine. We will come back to the continuation of it. But let me excite your, creativity by asking a simple question. What do these three things have in common? Three things are very well known. One, that if you cut your gut and invert it, you find that the entire inner surface is layered with small tubules like structure called as microvilli. Similarly, a concept which possibly of 1.4 billion people in India, 1 billion would be knowing for sure, mitochondria, which is also called as the powerhouse of the cell. If we cut the mitochondria which is present inside the cell, we find that there are these enfoldings like structure. And the third thing is the Turkish towel that you use on a daily basis as you take bath. What is common to all of them? People, I think it should be quite evident that the entire towel that we have has got multiple loops of the thread, which I believe now you can visualize is exceedingly similar to what's there in your intestine. Rather, let me tell you, the structure of this towel is inspired from that only. This is called as biomimicry. In each of these examples that we took, those loopings allow to increase the surface area of absorption. Here the food, here for the energy production, and here for water from your body. This year's Nobel Prize has been awarded for developing the materials which have got exceedingly high degree of surface area in the least possible space. So much so that the material developed, you can imagine, has got over 7,000 square meter area in the material of just 1 gram. Or if I can relate you with something that you need not do the quantitative measurement, 1 sugar cube size will pack within a surface area of 6 football fields. Imagine the material would be of high utility with respect to the huge surface area that it has to offer. So let us start as to what is the work that these people have done. Now, other than the increased surface area, these materials people, they have got huge porosity. They are extremely porous, just as the piece of sponge block that you may visualize, or the pumice stone which might be used to exfoliate from your skin, or these natural loofah which if at all you might have used, which are nothing but the dried skeleton of the gourd vegetable that we consume. Each one of them, they also have huge porosity inside. So other than the surface area, they have got huge pores or many number of pores inside, of course contributing to the increase of surface area itself. There are multiple materials which are porous in nature and are classified into different categories like based on the size of the pores: microporous, mesoporous, macroporous. Micro is the less than 2 nanometer size pores. Meso is 2 to 50 nanometers. Nano is 10 to the power minus 9 meters, you must be knowing. And macroporous is greater than 50 nanometers pore size material. Now, this story of the Nobel Prize starts majorly in 1990s when Mr. Richard Robson, one of the laureate, an Australian who did his work in America. Now what he did, he created the coordination compound with the copper ion. There I had showed you with some metal, let's say iron, and connected to the copper, just keep the matter simple, is the organic ligand. Ligand is anything which is connected to it by the coordinate bond. This organic ligand people could have shorter structure or longer structure also. You remember when I described the organic cyclic molecules, I did show you these organic molecules can be of various size and structures. Can you see? It could be shorter, it could get longer and longer. So, these metals, Mr. Richard Robson, copper metal was connected to various organic ligand, and there he created a pyramidal structure. He was very fond of diamond and the diamond shape. Now Richard Robson, he was experimenting if this coordinate compound is joined together, many of them, what kind of structures are we getting? Let me tell you that Mr. Robson, he expected that when he will connect this coordinate compound n number of times, can you see this one thing connected many number of times, he thought that the structure would be non-crystalline, it will not be like a crystal. What is a crystal? A structure with well predictable shape. So he thought that it will be amorphous without any particular form. But much to his surprise, when he connected these pyramids, he did get a well crystallized diamondoid structure. Diamondoid means diamond like. Oid is the suffix for like. Humanoid, robotoid, tabloid, android, organoid, like that. So diamondoid structures were created. So this was the structure he could generate. It was a major find at that time, let me tell you, because they all believed that it will be amorphous. He went one step ahead. He also understood that these crystalline structures created of metal with the organic ligand, repeated many times in the different dimensions, the length, breadth and height in the 3D, would create a well predictable crystallized structure. That's one. And he further established in these crystallized structures there would be a lot of pores in it, pockets, and he suggested that these pores or cavities could be used for filtration. So we could filter those stuffs which are very tiny and otherwise it is not possible to the macro devices. Fine enough. This matter of developing the polymeric three-dimensional structure was taken forward by the other scientists also. For example, Susuma Kitagawa and Omar Yagi. What did they do? Both of them then started taking many different metals and many different organic ligands and using that started creating multiple different structures. For example, Kitagawa started creating multiple three-dimensional structure with copper atom connected with the organic material. Mr. Yagi, he started doing with cobalt and zinc, nothing of that to be remembered, just know different metals and different organic ligands. And in doing that, what they realized, that they are getting multiple different 3D structure. I have got a very good video clip which the auto suggestion on my screen was showing the toy. As I keep searching for my kid, they did show today a particular toy called as Shoshibo, shape shifting box, and it was again like a cosmic thing. I mean, it just occurred to me that we could use it as an analogy to understand what the Nobel has been given for. Visualize this, people. This is a box that could be folded and refolded into multiple 3D structures. Each time, can you visualize the size of the hole is varying, and then you can see how the different structures by merely different orientations and foldings could be created. This is called shape shifting box or Shoshibo. I am quite enticed by this toy, by the way. Anyway, let us now understand that both these people, Yagi and Sushuma, they then started creating different structures which all had, can you see, different three-dimensional conformation. So they were all, by changing the metal and changing the organic ligand around it, they started creating multiple polymers. Polymers is if you keep on adding the structure again and again repeatedly, they created of structures of different shapes, different pore size, and different properties. Further, Sushima Kitagawa, he also proved, bachcho, that if these structures are bonded by some elements, so let us say if inside this structure you pack up some other element, the structures are thermally stable. So what did he prove? He proved that all these structures, they are thermally stable, and if anything which has been put inside these pockets or pores, imagine if you are packing something into this. As we just understood by Robson's work itself, there are pockets in these 3D molecules, and within these pockets there are gases, any material, any metal that could be packaged, which is called as the guest molecule or guest atom, based on what stuff are you packaging. Kitagawa also proved that when these materials would be heated up, this structure will remain stable, but on heat, this material will get easily released. Keep this in mind. There is a very beautiful application that we are going to derive out of it. So that's one thing. And then Yagi went on to establish that there could be differences in the number of pores and the sizes of the pores. So Yagi, out of the three, Omar Yagi, he established that we can, by creating multiple structures, we can vary the pore numbers and pore sizes, and in it we tried achieving those materials which are extremely porous, so much so that he developed certain materials which may have, because of the number of pores, the surface area inside which is exposed almost this much, 7,000 square meters per gram. Wherein I told you at the initial part itself, a sugar cube may package inside it over 6 football field area. One last little thing. So what we have understood, the coordinate compounds, when polymerized in the 3 dimensions, may give rise to the structures crystalline, porous, of specific pore size, and then we found that these are stable to the heat, and anything that is fixed in the pore can be released by heating, and we can create the different pore sizes. Further, one last little thing which was important. But there are many porous substances like the pumice stone I did show, or for that matter, imagine there is this material called zeolites. These are also materials, chemical materials, but these are inorganic. But what are we dealing with? The organic ligands connected by the metallic clusters. So the problem with these zeolites, which are silicates of aluminium and all, they are also very porous. But remember, in case UPSC asks, zeolites are more rigid. Like I did show the stone through which you can exfoliate your heels. Unlike this, these structures that we have talked about, they are both a mix of rigidity plus flexibility. What does that mean even? Rigid enough to maintain its shape and flexible enough to be molded into different reversible structure. Like if you look at my skin, it is maintaining a particular contour. If I pull, it changes its shape, but if I release, it comes back to the same shape. That is called as being rigid enough to maintain the shape, but flexible at the same time. Kitagawa, that is one last little thing. Kitagawa did establish that these materials that they have created is flexible at the same time also. You can imagine a block of paneer that you can do a bit of structure shifting. And this would also allow you to package the stuff. Let us say in this we have packaged the gas, and by physical stress release these also. Can you see? By merely shifting, all these gas molecules get released. I believe you are able to connect that to what possible applications it could lead to. Bacho, these structures or these frameworks that we have created in 3D ultimately got to be named as the metal organic framework. This is what initially you saw in the title of the Nobel Prize. These metal organic frameworks or MOFs could also be called as porous coordinate polymers, PCP, because it is very porous. And what is the base material which is repeated again and again? The coordinate structure. What is coordinate? A central element bonded with the coordinate bond with the organic ligand around. So PCP. And bacho, these structures, they are today found to be extremely valuable for some unique properties that they possess. What properties do they have? One, of course, it is there in the name itself, and that could be the moot point that you have to remember. They are highly porous, and because of the porosity, they have a very high surface area. Remember any of the analogy that I gave you for the surface area comparison. Further, they can act as cage, and these cage can be utilized to store as well as release the various materials. And what all these materials could be? Any gas, water, metal, based on what size that material is of. So you remember that the storing and releasing both can happen, and hence it is a reversible cage. It is not something wherein if you have put something into it, it is permanently lost. No. And the fact that they are extremely flexible. Further, they can be made to be non-reactive. Non-reactive to who? To the guest that is occupying the space inside those pores. So they can be used again and again. Hence, reusable. So I hope you have understood this brilliant material that they have come up with. It is very easy to synthesize also in the lab, and that is why the utility of this in multiple areas is catching up like anything. I'll quickly talk about that. So what we have now understood is what are coordinate compounds, then how the polymerization of that leads to the 3D structures with beautiful properties called as the metal organic frameworks, and how because of all these properties, these metal organic frameworks of different structures and pore sizes could serve multiple purposes. So people remember, MOFs are something which look like rocks but act like sponges. So they are to appear rocky, but are spongy in nature. This is the list of huge number of applications it might serve. You can pause the video and take the individual ones, but let me highlight some important ones for you. Anywhere wherein the surface area or porosity becomes important, you can use it. So let us say one of the big problems that we have across the world is the availability of potable water or drinking water. Almost 1/3 of the world does not have access to safe drinking water. And then there are those geographical domains where the availability of water itself is a big crisis. You can see this map where darker the shade of red, you see easier it is, and lighter the shade, which is more and more desert. So you can understand how much is the coverage of the desert area, where in any way it will be too parched for the availability of water. Now through these metal organic frameworks, people, we are developing, and there are many companies that are working on it. Kindly visualize the left half of this circle. These cage-like structures in the desert area with humidity as low as 20% or 15% also will trap the water molecules that are there in the air, will gradually start settling in these pores. And I hope all of you know how the rain formation occurs. There is a nucleus formed, and around the nucleus more and more water starts concentrically growing. Somewhat similar to that, as the water droplet comes into this pore, more and more water will come, it will get saturated with it overnight. And the only thing we have to do is, in the next morning when the sun comes out, this particular MOF structure will then be put in the glass cage, because you don't want the water to vaporize back again. And as the water, the MOF gets heated up by the sunlight, all the more accentuated by the greenhouse effect because of the glass caging. As I told you, thermally, when you are heated, I told you earlier also, they will release it. So the same cage will get the water to drip out, collect and serve. The assessment says that one washing machine size of this device can very comfortably serve the requirement of one small family. Now I am not going to define the meaning of small here. And hence, people, it is going to be the next big thing for generating water in even those areas wherein there is not much, which could be somewhat very similar to the vaporators that you might have watched in the Star Wars. They worked on different principle. They worked on cooling the towers on which the water vapor can condense, but this is different. Anyway, but this is like sci-fi brought alive. Look at another. In 2017, Nature journal published a very important article. The article says 7 chemical separations to change the world. We do in chemistry lab, you might have done this distillation, when you separate two liquids with different boiling points. That is the crudest way of separating the different stuff. Today we have the better technologies, one of which is the MOF membranes. This article said that the game-changing separation is required in all these areas, hydrocarbons for crude oil, from crude oil rather. You see, for petroleum purification, uranium from seawater. Every time you talk about the radioactivity leakage, you'll have to separate the uranium atoms. Further, alkenes from alkanes, the different organic molecules. Greenhouse gases from the dilute emissions. So you can also separate the greenhouse gases from the atmosphere. Rare earth metals from the ores, which I hope all of you know is one of the biggest deciding factors in the different IR issues. Benzene derivatives from each other, trace contaminants from water, extremely important. If the water has got a lot of heavy metal pollution, we keep talking about Yamuna, cleanup. People, there are many stories covered around that, the water filtration. You see, there was this Hollywood movie, Erin Brockovich, which was all centered around how the lady develops cancer because of the chromium pollutant that is there in the water and brings the state to its knees for having faulted the citizen. I remember over a decade back, there was this, girl who became viral with her rap song, Kodaikanal Won't. So Kodaikanal Lake was getting polluted because of mercury, because there was a manufacturing unit for the thermometer which is supposed to be serving the US market. So she, put her foot down and it went into the court of law, and ultimately the company Hindustan Unilever had to take the entire 300 tons of mercury contaminated material back to United States. So today with this technology, our ability to filter water and depollute it would be much easier and much more efficient. So remember that pore size will decide that what all materials can be filtered, and what you want to filter will decide what structure you wish to create. I told you the flexibility of creating different structures, right? So there was this news that came up. After 15 years legal battle, Hindustan Unilever pays mercury exposed workers in Kodaikanal waste sent to US. So we know that this is a raging issue. There is another problem, people, that we want to find a solution, and that is the carbon footprint. And one of the solutions that we have been working out, and there is also exam relevant, is the carbon capture and utilization technology. Capture simply refers to, from the source of production, you collect the carbon instead of allowing to spread out and store it concentrated into those areas wherein it will not diffuse out. Those could be the deep sea storage, or at those pockets which are not going to be mined in future and are porous. For example, coal beds which are not mining to be mined in the future. You can keep your carbon dioxide stored through the pipelines from the power stations. Primarily the power stations generate the most massive quantity of CO2, and hence that carbon capture technology. Now people, that also has got a number of problems, because how much can you do this? The efficiency itself. The chances of, because of over storage, even initiating seismic activities, extreme, but yes. And hence we are today working on metal organic frameworks with exceptionally high capacity for storage of carbon dioxide at room temperature. This was a research article published by one of the Nobel laureate itself. And what Yagi proved, that in a one cylinder the quantity of CO2 that you can pack up is equivalent to what under very high pressure also you can pack up in 9 different cylinders. So such structures in the pore can store a lot of CO2 and hence could be also used for carbon capture. But so there is another aspect with the carbon capture which is exam relevant that you might be studying. If somehow we can also control, release those carbon when required, which could be used for synthesizing the fuel again, that is called as e-diesel. It would be extremely useful to release these carbon for that purpose also. And I think all of you already know that we have discussed the binding of the guest into the pore is a reversible procedure. So obviously there is added utility that it comes with. So metal organic framework will have extreme importance in the carbon capture. There was this image that was taken in 2017 that became quite popular. This is one such, I'm sorry for the little hazy image, I could not get the high resolution. And then in this, when they did the microscopic study, they found the carbon dioxide molecule which was trapped. So they could figure out that yes, it is a good entity for carbon dioxide trapping. Then there are many other applications. These pores, people, could be used as sensors. You can have certain sensor for certain toxic gases, and you can use it in those areas where in the mines wherein people are working, and because if any toxic gas goes and binds to that sensor, it will start throwing up the light. Capsules could be created with great space for packing the drug inside, so it could be very good tool for drug delivery inside the body, right? So you see a lot number of, and can it be also used for having catalytic reactions, because all the biochemical or chemical reactions, they require catalysts. More surface area will allow more chemical reactions to happen on those catalysts, and hence accelerated catalytic industrial procedures, enzyme making, drug making, antibiotic making. So it opens up the entire huge world of applications. Now let me show you that this award has been so timely. There is this one of the market analysis that says that with the compound annual growth rate of 40%, there will be 30% or 30-fold rather, increase in the market potential by 2035. Within 10 years, whatever market size that we have for the MOF, it will be 30 times that, certainly establishing that this award has been so very timely. And so very correct for the work that they have done. Wonderful it is. Now towards the end, let me express my personal ways of looking at the Nobel Prizes. Every year when the Nobel Prize gets awarded, other than of course the science involved in it, I really find extreme pleasure and satisfaction in listening to those audio clips of the call that goes to these scientists. I mean, I would advise you in your spare time, you can listen to them. They throw a lot of life's wisdom in that couple of minutes of talk as the news gets unfolded to them. So this year also there were some good messages that those, I am not bringing the audio here, it will consume a little more minutes. So this Japanese, by the way, have you noticed over the last few years, Japan's footprint in the Nobel award list is increasing, I mean, by leaps and bounds. It is going, it should be considered as a good case study, so that we could, take some notes home and try replicating the model for our better performance as well. So you see, Susumu Kitagawa, he just made a statement. I tell my students that challenge is very important in chemistry, in science. I believe he could have added in life as well. So you take the challenge, there is a problem, and of course I believe that humans over the few millions of the years have proven that their indomitable spirit can surmount any challenge. There is this interesting thing that came up. I mean, when Mr. Richard Robson got called up, he exposed that when he was working initially, his idea was not something that garnered a lot of support. He says some people thought it was a whole lot of rubbish, and then he also disclosed that he never wanted to study chemistry. Rather, chemistry happened by cosmic design. He always thought that the real studs study mathematics. He considered mathematics as the biggest of all subjects. But as luck would have it, not only did he study chemistry, but he has ended up winning the Nobel. But the real show stealer for me has been the third one. Someone born in Jordan, and he happens to be a refugee from Palestine. And interestingly, he did not have any of the early prerequisite that we think of in the child's life when we try to plan everything for a bright future that he could afford. It was a family of 12 members, he says, and along with the cattle, they stayed in one single room. His parents were not educated. The father was just 6th standard, maybe hardly literate, and mother, no literacy at all. And this fellow goes on to win the Nobel. I mean, we cannot have a bigger story than this. So when the call was made to, Mr. Yagi, he was about to take off in the flight, and it just occurred to my head that he must certainly have got more number of wings in that flight, and someone who would literally go into the cloud 9, other than figuratively, of course, as well. So he made a statement which is what I will leave you people to munch upon with. He says it's quite a journey. Science allows you to do it. Science is the greatest equalizing force in the world. And by here, science, you just mean be a seeker. I mean, if you chase knowledge, I think it can take you from wherever to whichever place that you aspire to go in the life. I just hope the entire discussion has made sense to you. This will remain important from the exams perspective also. I will try to revisit for some other important discussion. Till then, take very good care. Thank you.